Yeah, thank you. I want to thank the organizers for inviting me here, especially because I haven't been working on water at metals or electrochemistry in a long time, and still they had some faith in me giving something relevant. And I hope to be able to live to the expectations. Before we start, I'm at the University of California, Davis is about an hour flight north of here near Sacramento. I'm in the Department of Chemistry, and you may know that in the United States, surface chemistry is not chemistry, it's chemical engineering. But I still do some surface chemistry in a strange way, because I have projects on related to the environmental and environmental atmospheric chemistry, and we study molecules at high surfaces, photodissociations of molecules at high surfaces, and these are other projects that we have that I put under the label of Earth and Environmental Chemistry. We look at crystal nucleation and growth in various environments. This is, for example, high pressure, high temperature diamond from the liquid. My background is more in material science, and I have a whole bunch of projects in my group that go through materials discovery. And we did a lot of work on thermal transport, which is perhaps the topic that I developed the most in the last 15, 20 years. And then this is just trying to give you an overview of what we do in the group. I have a box where I put everything else. That is some fundamental understanding of matter that goes from non-equilibrium dynamics of fluids, so ultra-fast response to pulses, laser pulses, and we do some methods development. So I hope from this portfolio that I have managed to find something that might be relevant to understand this difficult problem of electrochemistry and characterization of the double layer. I don't think I have to explain this to you because you know much better than me. What I want to stress is that this is an incredibly important problem also in environmental water chemistry, because this is how these processes at the interface control the dissolution or crystallization of minerals in the environment. And so you may have a situation where you have in the Stern layer here, you have accumulation of ion and chemical reactions and so on. And when you start simulating, this is a paper from Clotilde's group, and I think this is more or less state of the art of the kind of systems people simulate now by first principles. You are somewhat limited in the size of the systems you're simulating. You can try and put something else. I mean, this is with periodic boundary conditions, but you can put the virtual electrode or whatever else, but you're still in the nanometer scale, whereas the diffuse layer we were talking about this morning can go all the way to tens of nanometers or even longer, so it might be relevant. And one thing that can happen is that you get an ion accumulation at the layer in a small cell, and then the counter ions, then there is a disbalance in the concentration at the counter ion. So what I would argue is that perhaps what I'm showing you today is relevant because this can be seen as an open boundary problem when you are simulating these systems of electrolytes near an electrified surface at the small scale. Where I got there is a different type of problems. I have been interested in nucleation and crystallization for a long time, and something similar happens when you try to simulate the crystallization in solution. You have your supersaturated solution where here the red spheres are the ions, and then you try to drive crystallization in a way or another. And since the system is relatively small, this is what you can afford in your simulations, you start having your concentration is not constant in the system, because now the growing crystal doesn't contribute to the actual concentration of your solution. And you see the formation of a layer around the crystallizing embryo, that is called a depletion layer where you don't have ions. So this is changing completely basically the free energy surface or the driving force to crystallization, and you cannot be quantitative if you want to estimate, for example, nucleation rates or growth rates and so on. So this is pretty much the problem that got me into this kind of open boundary system. So in principle, you would want to compensate. So the chemical potential of your solution is changing, and you would want to compensate by introducing more ions. If you do that in a condensed phase, so it's a solution, if you try the traditional particle insertion method, that always fails because the acceptance rates are very low, because you end up always overlapping atoms to your solvent. So one thing I worked, and this is now embarrassingly long time ago, was to try to simulate open system through adaptive resolution simulations. This is something that started, I would say, this is the first stone in this building of adaptive resolution from Matej Paprotnik, Luigi De Resita, and Kurt Kremer in Mainz back in 2005. The idea is relatively simple. Conceptually, you want to couple an atomistic system, a high-resolution system, to a coarse-grained system, for example, to simulate liquids or polymers or whatever, molecular liquids and so on. And the coupling happens smoothly through a hybrid region. But since this is a liquid, you have molecules that go from the high resolution and transform into the low resolution ones. And the way of simulating that can be pretty tricky. The first approach that was devised by these folks here and friends was to interpolate the forces, basically, to change the way you evaluate the forces from one side to another. And the way they wrote it, they set it up, actually it was proven could not have a Hamiltonian. So what we did, oops, I'm going back, sorry. So what we did was like, okay, let's go back and try to make it Hamiltonian. So instead of interpolating forces, we said, okay, we can write a Hamiltonian where we have the usual kinetic energy, we have the interaction, the internal degrees of freedom of the molecules that are what they are. And then we have the, let's say, non-bonded interaction in the language of force fields that can be calculated at the atomistic level or atom level and the coarse grain level. And we have a switching parameter, this lambda here, that is equal to 1 in the high resolution part, and it goes to 0 in the coarse grain part. So this system is now Hamiltonian. The only problem is that when you take the derivative, you have a term, this term here, that is the gradient of this lambda function. This lambda function is a function of the coordinates, the absolute coordinates in the cell. And so there is this force that is sometimes called spurious force or drift force that drags particles from one side to another of the interface. So if you simulate that Hamiltonian there, and this is the equation of state of the, let's say, all atom part, and the equation of state pressure versus volume, so inverse of density of the coarse grain part. They don't overlap, of course. And you get something that is somewhat random. You have typically a densification a high density in the all atom part and a low density, a depletion in the coarse grain part, and some mess happening at the interface. So what you would want is to control the pressure or the volume. You cannot have both if you don't have a perfect match of the equations of states, and have either the same pressure or the same density all across the system, right? So we found out there was a program similar to this several years ago at KITP in Santa Barbara, and with a bunch of people we sat down with this problem, and we're like, oh, well, we can think of these as a sort of thermodynamic integration problem. So you have a molecule that starts here at high resolution and evolves there at coarse grain, at low resolution, through a boundary region where it changes smoothly, and it is, in every point of the hybrid region, of the boundary region, it will have a certain position and a certain value of lambda, right? And if you look at the spurious force that we had before, if you take the average of that in that position, it takes this form here. So this is the angles indicate an average for this little slice, which is exactly what you have is the thermodynamic force in a thermodynamic integration expression. So we can take our system, simulate it at this hybrid resolution in a full cell, and calculate this average force, and recognize that this is the derivative of the free energy of going from here to there in that point. So yeah, this is exactly what I was telling you. Now, we can think of that and say, okay, we can compensate the effect of the transition force, of the drift force, through a term that is still Hamiltonian, and it is calculated numerically as I've shown you, which is compensating the free energy. So that's what we call the free energy compensation term. We calculate it slice by slice, and we apply it in the opposite direction. So we can spline it and send it back. And if we want, so this, by construction, will compensate the Helmholtz free energy. So it will make a system, will give you a system where you have the same pressure everywhere, but since you have a difference in chemical potential, you have a different density. If you want the same density everywhere, you add a pressure, a term delta P that depends on lambda over the average density, and you compensate the Gibbs free energy. So depending on what you want, you can design your compensation term to have either the same density or the same pressure everywhere. So this is pretty nice on paper. When you implement it, you find that to work. We started with some ideal systems, and then we went to more realistic systems in the years after. This is a paper from 2016. There was a massive implementation effort of Maziar Heidari, who was a student at the Max Planck, to get it into lamps. So here we have water and a coarse grain representation of water. The blue line is the pressure, and here is the density without the free energy compensation term. The green line is when you want the same, if you apply the density compensation, so the Gibbs compensation, so you have the same density everywhere, not the same pressure, of course, and the red line is the constant pressure compensation, right? So this works for water. In this case, something we realized is that in a system like this, well, when the implementation becomes complicated if you have like water and you want to implement long-range electrostatics, but we could get away with this trick by Dange-Zelter's group. This is this damped shifted force method that kind of gets in the long range as a mean field effect and doesn't calculate the long range, which is many body. Now we're interested in solutions, so we have a multi-component system. This is just the one before was just a single component system. So for a multi-component system, we went to look at the binary mixture in a ideal system. And if you do the math, it's very simple. You realize that for every component, we have components A and components B here. You end up writing a Hamiltonian that is I mean, it's the sum of, is an adaptive Hamiltonian for each of the components. And the compensation term ends up being just additive. So you can calculate the compensation terms from simulations of the two-component system, just looking at the contributions of each separate free energy. So you just do a single thermodynamic integration of the homogeneous system at the desired conditions, and you evaluate the compensation term. Now, this was our first release of this type of work. What you can do now, we have a sort of self-consistent approach that does it automatically on the fly, and it gets you the compensation term in a few thousand molecular dynamic steps. Now, how it works, so let's take a mixture of where we have the gray particles and the orange particles, and they all are coarse-grained by the same blue particle. No chemistry here, just colored particles, right? And this is remarkable. We can use the same coarse-grain model for both, which means we can also do like a semi-grand-canonical switching in the coarse-grain part at zero cost. And so this is what you get. This is a representation of the system. The high resolution region is the central part, and the low resolution region is these two parts here. Without the compensation terms, you get an accumulation of the orange particles in the center. When you switch on the free energy compensation, you manage to have the same density with some wiggles in the hybrid region. You can get rid of them with the newer adaptive scheme or self-consistent scheme, but doesn't really matter so much. And you have the desired relative density, relative concentration all across. So when you are interested in what happens in the high resolution region, if something happens that is changing the chemical potential in the high resolution region, then the free energy compensation method will drive in particles or drag out particles. Okay. This is just showing that you get the local structure is exactly the same whether you do a full atomistic simulation or these hybrid simulations here. I didn't do much in this direction anymore after those works that I have shown you. What the group, Kurt Kremer's group with Robin Cortes-Huerto went on working on that. And one of the ideas that we developed towards the end was, well, since one can couple the system to any kind of coarse graining, you can even couple it to the ideal gas. And they recently shown that this coupling to the ideal gas is formally a grand-canonical ensemble. I mean, represents formally the grand-canonical ensemble for the all-atom region. This is a recent paper. One thing we did was to try to transfer the idea to adaptive QMMM, which has now the problem that you don't have pairwise or multi-body forces. You have a many-body potential. So here we were thinking of, well, if I want to look at the solvation shell of an ion and simulate the ion, or this is just a water in water, but simulate the molecule at quantum mechanical level, and one or two shells of solvation at quantum mechanical level, and then the rest classically, right? You can write the problem in the same way, but so where you have the quantum, the classical, and then the intermediate, the hybrid zone or the transition region interactions. But now the transition region is a little complicated to represent because you have to calculate at quantum mechanical level all the possible permutations of the molecules that would contribute to the QMMM potential, basically. So that is all the permutation where you have a particle, and these are labeled, but let's say the ion you want to solvate, or the quantum mechanical region is quantum, and then you have quantum molecules in the hybrid region and a molecule at the MM level in the outside. So in principle, all these in this simple 4-molecule systems, all four permutations P1 to P4 should contribute to the QMMM, and these two outside do not, because you have, of course, you don't calculate the quantum molecule outside here or a classical molecule in the quantum region. So this actually would scale in a combinatorial way. So it would become very impractical when you have a lot of molecules in the hybrid region. One thing that might simplify things is to write this and say, okay, I take only the ordered ones. So I would take, I consider 0 the contribution of permutations where we don't have a certain type of ordering. So we calculate only these first two here. But still, you end up with a representation where these are the weights of each permutation. The weights of each permutation depend on the weights or the quantum character of each molecule here in all the permutation, and this is the expression of the QMMN force where you have this transition region contribution. And you end up with the same problem that we had in the classical case, where you have a derivative of the weights with respect to their to the position of the molecule. So you end up with this spurious force again. The compensation for that, so this was something that had already been explored by other groups. So what we did actually is to derive the compensation term, and the first thing we did to derive a compensation is just, okay, align the potentials of quantum and classical, which at least should give you the right densities in the quantum and in the classical region. Now the problem is that in the transition region, you end up just aligning the energies, you end up having sort of a potential bump that leads to a depletion here. So this is the green case. If you do the same trick as I showed before with the thermodynamic integration, you can write a compensation term that comes out. This HC is the equivalent to the thermodynamic integration term that I showed you before. And with the thermodynamic integration, you get a density profile or a radial distribution function, in this case, if you are doing water in water, that resembles the one of the reference system that is non-adaptive, okay? So this kind of idea can get you toward a sort of adaptive QMMM that might allow you to treat let's say the layer near to the surface at a quantum level and the rest of the system, if you want, doing it classical, although I don't know how practical this stuff is. Something that becomes practical or more practical is if you do a good embedding in these adaptive QMMM models, you get, everything gets much simpler, so you can also reduce the size of the transition regions and so on. And with machine learning potentials, these are the natural choice for embedding at this point. So if I fit a machine learning potential that gives me pretty much the same energies and forces as my reference ab initio, then I can really implement this adaptive method straightforwardly. So this is an example where we fitted a neural network potential. This is a new revolution potential to RevPB0D3, and well, this was just to show off that we get the pretty good representation also of the experimental density anomalies and a lot of thermodynamic properties. With these large machine learning potentials, you can simulate very large systems to the point that in this case we managed to calculate the melting point with like a 10,000 water molecules two-phase simulation cell. So this, I don't think, needs explanation. We have seen a lot of this stuff already in this workshop. There was a question, there was some comments also in Julia's talk yesterday. It was like, so what, can you go back? Yeah, well, you can go back. If you use these machine learning models for sampling a relatively small system, then you can go back and do electronic structure. So that's what we did, for example, to calculate nuclear quantum effect on the electronic structure of water and ice, comparing classical molecular dynamics and path integral simulation. So this is pretty much where we started from. There was already some literature about it, actually very nice and very accurate work by especially Alfredo Pasquarello's group, where they evaluated with GW the fundamental gap of water out of a comparison between molecular dynamics and path integral simulation. We found, and they found a very large effect of nuclear quantum delocalization on the electronic structure. So this is also relevant, I would say, to this community, because it's like, okay, we have a complicated system, we are simulating it by first principles, but still the ions are classical. What happens when you go quantum? Well, you may have large differences in the electronic properties. Even larger have been found in ice. This was an estimate by Richard Neath's group from lattice dynamics calculations. So we had two scopes in this work. One was to get this data on equal footing, let's say, so doing everything molecular dynamics and path integral. And the other idea was like trying to understand why this happened, why is such a large, there is such a large difference in the nuclear quantum effects on the electronic structure of ice and water. So we did the calculation, again, comparing path integral and molecular dynamics, and having a good, actually two good machine learning potential. One was a deep neural net, and the other is new revolution potential. Fitted also on two different density functional theory representation. The NNP was fitted on scan, and this is on a hybrid. It's encouraging to see that the results are compatible. They are in good agreement, even though we have different architecture in the neural nets and different training. Some numerical differences, but the main result is that we see the reduction of the energy gap as predicted in the previous works, both in ice and in water. This is slightly different from the estimate by Richard Neath, but somewhat compatible within one error bar. The other thing we could look at is the main effect is on the position of the valence band. So we have a lifting of the valence band and not that much of a change on the conduction band. And then we try to connect to the structure. So what is the structure that is driving this change? What is the change in the structure that is driving the change in the electronic structure? So we look at this proton transfer coordinate that tells you pretty much how much a proton is delocalized between two oxygens. And this is the distribution here, and it is plotted against the distance among the two oxygens in a hydrogen bond. And this is for all the systems, but we can just compare the first four plots. So on the left, we have water, and you see this is classical water. The distribution is quite narrow. The 0 point of this distribution is when you have a proton going all the way or across the midway in the hydrogen bond. When you switch on quantum effect in water, you have a certain tail of the distribution going past the zero line. So we have an enhanced delocalization, which is what we expect. The comparison, something similar happens in ice, but in ice, the effect is so much larger. So the delocalization of the proton, let's say the fluctuation of the proton is much smaller in the classical than in the water case. And then the delocalization becomes larger when we switch on quantum. And you see here as well with this other potential. So we found a correlation between the delocalization of the proton and the amplitude of the band gap. This is the band gap calculated at hybrid level, but we had some also at GW level. It's pretty much the same. So we have this correlation between delocalization and closing of the band gap that is affecting the band structure, basically band structure renormalization in water and ice. And so this is just a perspective of what you're doing now with these tools. We are looking at some complex surfaces and interfaces. I was telling you about my activity on environmental chemistry in water and ice. We're looking at the surface of ice, similar work as what I've shown you. We are also trying to look at chemical reactions with machine learning models. It's quite tricky, and fitting very accurate models for electrolyte solutions. Now, going back to open systems, as I mentioned, we have, I showed you all this adaptive resolution work, which is very nice formally. It's a real pain to implement. So we wanted to find something simpler that could give us pretty much the same effect for the crystallization of, for example, for the crystallization of an electrolyte solution. So this is pretty much the system that we want to simulate. This is also looking by chance like the systems you guys are interested in, right? So the electrochemical system. So we have, the idea here is to basically enable this pseudo-grand-canonical simulation using an osmotic pressure membrane that will move and keep basically keep constant the chemical potential of the solute within a certain region of the simulation box. So we start from the expression for the osmotic pressure in this situation that depends on the molecular fraction of solute over solvent, right? And if we make some assumption for an incompressible and dilute solution, we can simplify. We like take the first term of the Taylor expansion of the log. We have the osmotic pressure is simply, and this V is the molar volume of the solvent. So at this point, we have for an incompressible solution, we have simply the well-known Van 't Hoff formula RTC. So we have a direct connection between the osmotic pressure and the concentration of the solute, and through the link between the chemical potential and the activity, where the activity is also a function of the mole fraction of the solute, we have a direct link between the mole fraction and the chemical potential. So this is the basic idea that we want to implement. So at a constant osmotic pressure, the mole fraction becomes an invariant, and then the chemical potential of the solute will be constant. So that's the idea. So we were implementing this as a restraining force. So the membrane is, by our choice for simplicity, so this is the general form of the restraining force on the osmotic pressure is the gradient of a potential, and we decided to use a flat bottom harmonic potential where with this expression here, where the small r is a reference point of the is a reference for the atoms, and r is the position of the membrane. So we have these expressions for, we have different expressions for R in the different geometries that we have implemented. So we can simply refer R to the, in 1D or in confining in 2D. So we get a cylinder, or confining in 3D, and we get a sphere. They're all pretty much equivalent. The nice thing of this is that it can be implemented as a Python script directly, for example, in any molecular dynamics code that works through a Python interface, like OpenMM. We implement the constraint, the motion of the membrane as a Berenson-Wick coupling. We don't want to have the fluctuations here. The fluctuations just make a mess. So we have a coupling parameter tau, And this is how we move the membrane. It depends on the shape we are using, but there will be an exponent that is 1 over the dimensionality of the problem. And then we just move it. We're trying to reach the target. We need to average so this osmotic pressure has to be an ensemble pressure, because if you use the instantaneous one, there are too large fluctuations, especially when you work at relatively low concentrations. So we average over, so there are a few parameters, a few knobs to tweak to make this system work. So we have this sampling length, that is the number of steps through which we estimate the pressure. And we evaluate the pressure every certain number of integration steps. And then, okay, this I said is implemented as a library. And the simplest thing you can test whether your thing works is you make a gas model like a Lennard-Jones, diluted Lennard-Jones gas. You start from high density and you equilibrate to a certain pressure in the, or for low density, and equilibrate in the various shapes. So this kind of proves that, at least in this simple case, it works. And we also get the same fluctuations in the pressure as in a periodic boundary condition simulation, or similar fluctuations. Now, this is the real test case we were studying, is the freezing of an electrolyte solution. So in rather simplified electrolyte solution, we represent water as with the single particle coarse grain NW model by Valeria Molinero and Moore, super famous for water now. And now we have 3 cases that we are studying. One is simply the crystallization of this ice-water system at temperature below the melt, so at supercooling. Same system with a concentration of sodium chloride ions at a pressure of 10 bar, corresponding to a pressure of 10 bar at the surface of the water. This corresponds to a osmotic pressure of 10 bar. And then this is our moving membrane, where we need much fewer ions here, and we set the target pressure as 10 bar, right? So we want to estimate the crystal growth rate of the ice as we drag the system out of equilibrium at supercooling, okay? Before doing that, we are testing we have to test those few parameters that I was mentioning. The coupling tau, we see that it's a good idea not to make it too small. This is in picoseconds, so 0.1 picoseconds is not good. You don't get a good distribution of the osmotic pressure. So this was tested with setting the osmotic pressure to 40, I don't know for what reason, but the idea is the same. The compute interval, you don't want to estimate the osmotic pressure too often. It fluctuates way too much. You don't get a good distribution, but then anything you choose larger than 10 is okay. Same goes for the sample length, is a little less sensitive, and there was an isothermal compressibility in the expression, or something that has the dimension of an isothermal compressibility, but also the algorithm is not particularly sensitive to that. It's just a scaling factor to the tau. Okay, the real results. So we have the pure water system. It crystallizes at a certain rate. You see that you can extract the crystallization rate from the slope of of the position of the interface as time goes by. Now, the system without pressure regulator is the orange system. You see that you can't fit a straight line here. You don't have a growth rate, and the reason is that simply when the crystallization front advances, the concentration of your solution is increasing in time, so it's suppressing crystallization more strongly. Whereas with the pressure regulator, with the osmotic pressure regulator, we have a long time range where we have a linear motion of the interface. So at this point, we can estimate the growth rates at any temperature. So this is just showing off. We can do a lot of simulations. But we can also calculate the freezing point depression when the growth rate goes to 0. And we see that for this model, we get a reasonably and unexpectedly good estimate of the freezing point depression. It means that thermodynamics of this model is pretty good, even though the model is very simple. If you compare our MD estimate, 2.13, to the experimental estimate. And it's linear, as it should be, colligative properties. Yeah, I jumped to my conclusions. Was in time, I hope. I showed you a few methods to simulate open systems, not strictly related to electrochemical simulations, but hopefully they can inspire you. Some considerations on machine learning, and I hope this could be useful. I think being here, my scope was to learn from you more than what you learn from me, and maybe like having cross-contamination ideas is always great in science. These are the students in Davis that helped me with this work, and a lot of collaborators through the years from the good old times in Mainz with Kurt and Raffaello, who is now in Trento. Rosa was at Utrecht University when we did the Hamiltonian Adaptive QMMM. Some recent work with, went back to work with Julia and Anne on ice and water. And the osmotic regulator was done in collaboration with Paolo Raiteri and Blake Armstrong at Curtin University in Australia. Thank you.